Okay, so hello everyone. Thank you for coming to this talk. My name is Konstantin Zolotov and I'm a senior Android engineer at Bumble. Since 2022, I have been working at mobile platform, and basically all I do is make other engineers happy. And today I want to share with you some hidden gems in Android build tools which can help you building your CI pipeline better. So I'll talk about internals of application building process, how your application gets compiled to the DEX bytecode. Talk about some internals, how Android build tools work, and of course show some practical applications, how can you use in your day-to-day life. But before we get to the problems, let's talk a bit. Sorry. I am terribly sorry. Something went off with my Wi-Fi, I guess. Oh, yeah, we're good. But before we get to the problems, let's talk a bit how your code gets compiled. So it all starts with the source code, Java and Kotlin, which then compile to JVM bytecode. At this stage, there might be, this one. Note that at this stage, Java and Kotlin compilers can run annotation processing tools. So it can generate some code or modify your code in some way that you didn't write, and then Kotlin compiler can also run compiler plugins, so the code internal representation will be different. Then JVM bytecode gets compiled to by D8 tool, gets transformed to DEX bytecode. Additionally, some libraries are included at this stage, and optionally there might be one more step where array tool optimizes the DEX bytecode and optimizes and obfuscates, and well, basically it is usually enabled for release and production builds, but disabled for debug builds. However, you can enable that for your build types in a way you want, and well, frankly speaking, Array is a more versatile tool. It doesn't work only with DEX bytecode. It can take JVM bytecode and convert it to DEX, and it can also just optimize JVM bytecode as well. So it's kind of platform agnostic. And why two tools, D8 and R8? Because they are different. Those tools are different. The main purpose of D8 is to transform JVM bytecode to DEX bytecode. D8 is a simple DEXer, so it can do some sort of very local optimization, like this one. This is obvious that else branch will never get invoked, so it is possible to remove it, but it's not the case for some complex optimizations. For instance, let's look at this function. Obviously, we have function grid called only from one place with non-null parameter, and D8 can do anything between several functions, but Array can do. So Array is a whole program optimizer which takes into account all the bytecode you have and does very, very interesting optimization. For instance, let's have a look. The first, name is never null, so we can remove else branch at all. Then name is always the same, so we can inline it, and you see on the first step the string is generated at runtime, but we can actually generate it at compile time because it is just one string that never changes, and it will be a static string, so you will the runtime will not do any string manipulation. And the third step is that the grid function is very small. It is exactly one function call, so we can inline it to save the space, to not handle one more function, to not handle one more jump, and just inline it. This is what array can do, but that's not all the optimizations array can do. But we will not delve into this today because it's just important to understand that that array can change your code very much, and array full mode does even more. This is a screenshot from the array documentation. For instance, it can remove the default constructors. Default constructors are just not something magical, it's just a special function. And if it is just empty default constructor, it will remove it. This function will not be invoked at all. And there are some other optimizations. Yeah, if you want, you can find array documentation and read the full mode. And this is where problems arise. Some libraries like JSON, retrofit, and some other popular libraries rely on reflection and rely on the fact that there are default constructors and maybe some other attributes. For instance, Android 13 parseable optimization was relying on the fact that parseable creator is an internal inner class in the parseable module itself. But array was optimizing that, and that optimization didn't work. And without special care, without special handling of the rules, special array rules, we basically can be sure that everything is fine, and we have to keep that in mind. And that's what happened. I think you have seen it in production. I think all of you have seen it. Well, at least I'm sure I have. So, and the things you have to keep in mind that debug builds are not the same as release, and we usually do not test release builds that much. When you update Android Gradle plugin build tools, something can change. For instance, array full mode was enabled by default in Android Gradle plugin 8 last year, and I think it was kind of silent because I found it only after updating the plugin, and when my end-to-end test failed, I saw that something is off. Third-party dependencies like libraries, they usually have their own set of rules bundled with the binary, and those rules are merged with your rules, and those rules can actually have effect on how your code is optimized. Basically, you just include some third-party rules into your app, and you just trust it. You trust that everything is fine. Of course, there is a lot of open source code, and it is the community does a great job of keeping track of it. But is it good enough? And common problems that configuring array rules and tracking changes is hard. It is really complicated. And you do not really know which build ended up in the which code ended up in the release build, because various build types, various source sets, it can be different. It's actually possible to track using Gradle configuration which modules have been compiled in which build types, but that is different. That is Gradle configuration stage. That's even before the build starts. And what can we do with that? We can analyze bytecode. But so here I'm showing that we have a lot of analysis. We have static analysis, which apply to the source code. We have unit tests that usually apply to the JVM bytecode. We have instrumented tests that usually test bytecode, but usually it happens on debug builds. And we do not do anything with release, usually. Well, of course, release manual testing. Sometimes end-to-end tests can be done on release builds, but that is usually not the case. That's not what we usually do. And inspecting the compiled binary is actually a direct observation without inspecting configuration and inferring how it should affect the final build. So inspecting the bytecode is what we can do to see what actually happens. But inspecting bytecode manually is very complicated. For instance, there is a tool called dexdump, which is bundled with Android SDK, and it can basically do this. It can give you a text file with all the instructions, the attributes of the bytecode that was compiled. But like around 50 megabytes of text files, which is usually not very, which is usually pretty much common for middle-sized application, ends up in almost 1 gigabyte text file. There is no way a human can read it in reasonable time, at least. And the good thing that you do not have to, because Android Studio and Android Build Tools is an open source project. You can find a lot of cool things here, and I found. So what is particularly interesting for us here is several projects. The first one is APK parser project, which helps parsing the APK, getting the DEX files from that. Smally project to read the bytecode, which is actually originally was written by enthusiasts in community, but Google, I think it is no longer maintained, and Google has forked it and now maintains in-house. And a RAID project to deobfuscate the builds, the obfuscated code. So this is how you can include it into your project. Yeah, keep in mind that the versions will change. They do releases, so APK parser and Android tools common, they follow the build tools. Yeah, they follow build tools version in Smally has and the RAID have their own version, so please check Maven before before picking the version. And let's create a sample project, the basic one, Compose obviously, because Compose is trendy. Yeah, to just have a look what we can do. So this is really the basic project Android Studio creates when you select Compose project, and here is just the main activity and greeting composable function. And this is how we can basically parse all the classes that we have in this project. So the first one is we're using zip file, obviously, because APK is a zip file. We can just work with it as a zip file. Thanks to Kotlin extensions that we can work with it simply, closing, opening streams, handling the errors, use function is cool. So actually the interesting thing is happens in map. So we're getting the zip input stream. Here we're basically getting the entry. So you see we are taking zip entries, listing them, filtering only files that end with DEX, DEX extension, and reading the stream. So on the line 12, you see DEX files, get DEX files, input, read bytes. This is how APK parser gets the DEX file and reads actually the DEX file. And it produces classes. And then we are using just classes. So this is function that reads classes from an APK, and this is how we can use it. So it doesn't matter APK or AAB, because yeah, when we just get entries, we get all flat entries and list all the files with DEX and with the DEX extension. And yeah, let's just print it and see what happens. So we will get this, well, roughly depending on the library's version and so on, but roughly it would be this. So fun fact that even the most basic Android application that you create nowadays using Android Studio Wizard contains more than 10,000 classes. All the libraries included, Kotlin standard library, a lot of Android libraries that are also included. So like this is debug build, 10,000 classes, the most basic application. And you see that the names are not quite familiar. So something else, slashes, this is the type descriptor. A type descriptor is a thing that represents any type in DEX and also in JVM. So L means that it is a reference type. There are some other literals that mean different things. So for instance, Kotlin text string kt would be just Kotlin text strings kt, and Kotlin generates the classes for top level functions with the kt suffix. And for instance, example main activity is what actually the main activity is. And here is the simple function to convert those type descriptors to qualified names we are all used to. So for instance, 11 line 11L is a reference type. For instance, V stands for void, Z for boolean, C for char. I don't actually know why these literals have been chosen, but that's what we have. And how can you make your life easier using that? Well, there are several use cases. For instance, the most obvious one is to build the diff between different builds. To use it as a quality gates, and I bet you can have some ideas to build something tailored for your CI pipeline. And to get a diff, let's introduce a simple change in the project. So here I will add class hello that and delegate to that class hello getting the greeting name. So basically, basically instead of just making passing a name to greeting function, we just first call hello function and get the greeting name. The function is simple. It just randomly returns provided greeting or another Android, but that's just a demo that we have another class and to see how it changes. So this is I'm showing how the diff can be calculated. So if we list all the types in the APK, so we can basically calculate the set difference between the sets. The ones that are present in the first set and not present in the second, they are removed. Vice versa, the ones that present in the second set and do not present in the first one are added, and the ones that present in the both sets, they are retained, so they are kept. Maybe they have changed, but the classes are kept anyway. So, and this is how we can do. So just using the function for getting classes, converting it to human name, it should be qualified name actually, and basically line 9 and line 10, and calculate those differences. And obviously print what we have. And this is what we have. This is what we will get in this case. So we have added the class hello. We have deleted nothing, so deleted classes are 0. And how can you use it? So the main branch, for instance, if you do the main branch versus pull request, you can check what actually changed. 30 new classes on a big feature, that's fine. 300 new classes, that is something off, especially if you don't see that much changes in PR. It can happen when you update build tools, libraries. For instance, I remember a case when I have included a library and the library was containing some rules that disabled obfuscation for Kotlin standard library. And we had like Kotlin standard library classes not obfuscated anymore. Why? We had to dig, but we see it. We see it now. Actually, you can list what have changed. Additionally, you can compare several releases just to have changes between the releases. Basically, a similar thing to what GitHub does between tags. If you select several tags, it can show you the pull request between, but you can see similar thing, which classes have actually changed. Well, were deleted or were added. You can also compare the same build, but release versus debug, and this can show you how good your obfuscation rules work. You can see which things are obfuscated, which things are not obfuscated, and basically how good your obfuscation works. If you have a lot of changes, then it's fine, because obfuscation means that the original name is not the same anymore. It is replaced with something short, still unique, but not human readable. And if you have a lot of these similar names, for instance, obviously activities are not obfuscated because they are entry points and they specified in manifest. But all the code that is not entry point and not JSON model or something like that has to be obfuscated. If it is not, maybe it's a maybe it's a reason to have a look at what happens there. And speaking about release, if we do a similar diff for release builds of the same changes, it will show this. Why? Because remember, I have shown you the how array can optimize the function. That's what exactly happened here. So the function hello is get greeting name in class hello is very small, so it just inlines and removes the classes. So we don't actually see it in release build, but if we still want to, I will add the special rule that keeps the class hello obfuscated, but well, which keeps the class but still makes it obfuscated. And in this case, applying this rule, we will have this. The obfuscated name, in this case it is obvious that this class is hello, but what if you have a few dozen of classes, maybe even dozen? It would be very hard to find out. Of course, when the build is done, you have a source map file in the build output, but those source map files are usually pretty big. For medium-sized application, it can be 500 megabytes, 400 megabytes, which is big a lot. And another thing, build's obfuscation is not stable. So in one build, one class can be obfuscated in one way. In another build, it can be obfuscated in another way. And that's why builds are not directly comparable. And that's why we need deobfuscation, which I mentioned previously. So this comes from a RAID project. We can read the source map file, and we can create retracer. Retracer is a part of a RAID project. So for simplicity, the diagnostics handler I will keep empty. ProGuard map producer is a thing that actually produces the ProGuard map because I mentioned ProGuard maps can be very, very big. You do not want to read it into memory directly, so that's why we use producer and keep source map to path. You can read it in memory directly, but path is part of Neo package. Well, it's extension that converts the file to Neo path, and it can read just using I/O, not reading everything into memory. And this is how we can use the deobfuscation. So we create reference from class descriptor. So in this case, I'm showing the name, obfuscated name from the previous example. And basically retrace class. Note that the API is designed in a way that we can have more than one retraced result. That's always simple for classes. For classes, there is only one. For classes there is either one class or no at all if the name is not right, if the name is not present, so it basically will return an empty string. But if there is something, it will always return only one class, because the type is the thing that uniquely identifies entity in the DEX. So yeah, this is API limitations, but it's not the case for functions. And yeah, for instance, you can have overloaded function, and function name is not the thing that uniquely identifies function, only function signature. So yes, and combined with the classes parser, we can do this. So we first get classes, create references from those types, and then using flat map to get the stream with results. For classes, again, always only one stream. Then we filter compiler synthesized classes, because compiler array can create synthetic classes, syntactic accessors, which we do not really care about. It's not that it won't work without this, but usually for our purposes, it's not what we need. We basically trust compiler that it generates the right thing, and we care about only code that we have originally written. So yeah, and then map it to qualified name again and build a set. And after applying this change, this is what we will have. The release build with obfuscated names, but we can still get what is the change. So another thing is quality gate. Another useful thing is the quality gate. So if you want to have a change list, maybe a set of things you always want to be obfuscated, or things you always don't want to be obfuscated. You can see if anything is obfuscated or not obfuscated, because you still can compare. For instance, you see the not obfuscated names, you can get the obfuscated names, and you see if the name before and after is the same, then the entity is not obfuscated. If the entity is different, then it is obfuscated. And if there is a violation of this rule, you can basically crash the build and I don't know, send a notification to developers that something is off, that they probably want to have a look at the pull request they're making. So this can be useful for the case I mentioned, when you include additional one more library and it provides a set of rules that affects your code somehow, you might want to review it. So also you can see if there is something unwanted. Usually we use different build types for debug, for release. We use some maybe feature toggles, debug menus, some other debug things. You can also build a similar change set and see if debug menu is not in the release build, and also hold the build if you need. So this is how you can verify that release build is good and some dependencies are not added to it. For instance, yes, I had also a case with this thing. I caught that a developer added test implementation into the test implementation dependency using implementation in Gradle. So it ended up not in test, but in actual build for the, well, in common configuration. So it's for debug, for release, and this thing just caught that this should not be here. This should be somewhere else. And yeah, developer could find it even without merging the pull request. So we proactively caught it. So also this is helpful while you're updating the dependencies and updating the build tools, because build tools can have some changes. For instance, last year Google enabled full mode. Maybe next year they come up with something else. And this is the thing that can also help you proactively track changes if something in your tools changed, and it can affect your code. So yes, basically that's it, what I wanted to tell you about today. Thank you for coming to this talk. Yeah, I'm not really active on social networks, but yeah, feel free to connect on LinkedIn, or yeah, catch me after this talk to talk about it or connect.